Alright, in this video we're going to talk about graphing absolute value equations. So this is assignment number 2 in Unit 2. And we're going to go ahead and get started by looking at an equation that's y equals the absolute value of x. And I'm going to use Desmos graphing calculator, which you can go to online. There's also a link to it on the home page of our course down at the very bottom. And so if we just start with y equals the absolute value of x, you might remember from Algebra 1 that it makes a V, but why does it make that V shape? And if we plug in -1, 0, 1, and 2 into the x value, because the absolute value means how far away it is from 0, when we plug in a -2, that's 2 units away from 0, so is +2. When we plug in -1, that's 1 unit away from 0, and so is +1. And 0 is 0 units away from 0. And so this point right here we're going to call the vertex, and that's at the point 0, 0. But then we have a point at 1, 1 and 2, 2, and -1, 1 and -2, 2. And so that gives us a V-shaped graph. But how does this change when we change the values that we are adding to the absolute value? And so, for example, here our original equation was y equals x, and we had something that looked like this: -2, -1, 0, 1, and 2 are the numbers we plugged in. We had 2, 1, 0, 1, and 2 are the numbers that came out, but now we're adding 2 to all of those things. So instead of 2 we have 4, instead of 1 we have 3, and 2, and 3, and 4. And so essentially what happened was it took the graph that we had, and it took every point and it slid it up 2 units. And so that's because we added a 2 at the very end. If this would have been a -2, it would have taken every point and slid them down 2 units. And we would have had a V that was slid down 2 units instead of up 2 units. So that's how a number outside of the absolute value affects the graph. But how about a number inside the absolute value? And so if we go back to our table of values, and let's say that we again wanted to get 2, 1, 0, 1, and 2 out of our equation, we would have to have something here that the absolute value would be a 0. And so how do we get the x minus 3 to be a 0? Well, we'd have to plug in the number 3, because 3 minus 3 is 0, and the absolute value of 0 is 0. That gives us the vertex. And if we plugged in numbers around 3, like let's say 2 and 4, if we plug in 2, then 2 minus 3 is -1, but the absolute value of -1 is 1. And if we plug in 4, then 4 minus 3 is 1, and the absolute value of 1 is 1. And we can plug in 1 and 5 also, but what happens is our original graph, which looked like this, everything is slid over 3 units to the right. And that's because this is x minus 3. And so the number on if the x is by itself here, when we're subtracting 3, it actually slid it 3 units to the right. If this was the absolute value of x plus 3, then it would be just the opposite. Everything would get slid 3 units to the left instead of to the right. So let's take a look at this in a different context where there's a number in front of the x value here. Again, let's start by assuming we want to get a 0 here for y. Well, in order to get a 0 out for y, I'm going to have to plug in a -4 for x, because 2 times -4 gives me -8, and -8 plus 8 gives me 0. And so what I'm essentially looking for to find the vertex, which is a key point to graphing these equations, is what can I plug into the absolute value to make it equal to 0. And so here it's -4, and you can see if I plug in other values around -4, like -3 and -5, if I plug in -3, then 2 times -3 is -6, and -6 plus 8 is 2, and the absolute value of 2 is 2. If I plug in -5, I'm going to have -10 plus 8, which is -2, but the absolute value of that is also 2. So you can see this number here not only affects it moving left and right, but it also changes the shape. Instead of going over 1 and up 1, which would put me here and here, as I did in the original absolute value equation, it made the slopes of these lines twice as big. Here the slope is +1, but here the slope is +2. Here the slope was -1 because it's down 1 and over 1, but in this line the slope is -2. So this number here also affects the slopes of the two parts of the v that make up the absolute value equation. So let's move on and talk about what happens when we multiply the absolute value equation by a number. And so you can recall that when we first had y equals the absolute value of x, we plugged in -2, -1, 0, 1, and 2. But now, and when we did that, we got 2, 1, 0, 1, and 2. But now we're taking all of these values that we get when we plug them into the absolute value and we're multiplying them by -2. So the 2 would actually become -4, the 1 would become -2, 0 would stay 0, 1 would become -2, and -4. And so the v is not affected by this number on the outside, the vertex is not, but the shape of the v is, because it's opening down, because it was negative, and it's also twice as fast, opening down twice as fast as what it was in our original equation. So now we want to put all of those ideas together in our general form for absolute value equations, which looks something like this. The first thing we want to do is figure out how do we find the vertex. And there's two parts to this. We talked about how the c value moves the graph up and down. Well, that affects the y value. And so the y coordinate for our vertex is always going to be where c is. And then how do we figure out the x value? The x value is what moves it back and forth. And we know it was a combination of the m and the b that did that. It was whatever makes inside the absolute value equal to 0. So it's whatever makes the mx plus b equal to 0. What value of x makes it equal to 0? So if we were to solve this equation here for x, we could subtract b from both sides and get that mx equals -b. And if we divided both sides by m, then x would equal -b over m. And so that gives us the x coordinate for the vertex. And so this is how we can always figure out where the vertex is in an absolute value equation. Then we talked about the slopes of the v's. In our first equation, the slopes were +1 and -1. But then they were changed, and they were changed by two numbers. They were changed by the m, and they were changed by the a. And they're both scalars. So multiplying the a and the m together would give us a combined change in their slopes. And so if we multiply a and m together, it's going to be plus and minus whatever we get, and they're going to be the same. Like if this has a slope of +2 here, this would be a slope of -2. If this was a slope of +3 on this side, then this side would have a slope of -3. And they're always going to mirror each other because this is an axis of symmetry going down the middle of those graphs. That'll always give us the slopes. And then we can also figure out whether it opens up or down, because if the a value is positive, we know it's always going to open up. And then if the a value is negative, we know it's always going to be a v, the shape of a v that opens down. So let's apply that knowledge that we now have to graphing an equation in that form that looks like this. The first thing that we're going to want to find is the vertex. And so we can find the x-coordinate of the vertex by using that equation, -b over m. And in this case, the b value is -4, so that's +4, over the m value, which is 2. And so 4 over 2 is 2. We also know that the c value, which is the 3, always gives us the y-coordinate for our vertex. So when we're graphing this equation, we know we're going to start at the point over 2 and up 3, which is right here. But then we want to figure out whether, first of all, whether it's going to open up or down. And because the a value is negative, we know this is going to be a v that opens down. But how fast down is it going to be? What are the slopes of these two lines? And so to find the slopes, again, we're going to multiply the a and the m together. They're both 2, a -2 and a +2, and if we multiply them together, we get 4. And so our slopes are going to be plus and minus 4. And so one of those would be going down 1, 2, 3, 4, and to the right one, and then going down 4 and to the left one. And they're going to be mirrors of each other. And we would know that we would get a graph that looks something like this. We could do the same thing using a completely different method, and that method would be simply to change the absolute value like we did when we solved equations. If you remember right, when we solved absolute value equations, we wrote two separate equations once we isolated the absolute value. Well, we can use that same process when we graph these equations. We could simply write it as y equals -2 and then change the parentheses here to, or the absolute value to parentheses, and go 2x minus 4 plus 3. Or we can write it as y equals -2, and we can change what's in the absolute value to negative, so -2x plus 4 plus 3. And then we can solve both of these equations and get it into slope-intercept form. For example, over here, if I had y equals -2, I would distribute the -2, and this would be -4x plus 8 plus 3. And so in slope-intercept form, we're going to have y equals -4x plus 11. And if I did the same thing to the equation on the right, I would have positive 4x and then minus 8 plus 3. And so that's going to be y equals positive 4x minus 5. And so if we were to graph both of these lines, the first one has a y-intercept of 11. So I would go up. It's going to be kind of tough to do here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the slope is -4. And so from 11, here's my first point. I would go down 4 and over 1. And then again, I would go down 4 and over 1, which would put me here. Notice that this is the point 2, 3. And I can continue to go down 4 and over 1, but it's going to give me a line that looks something like this. If I graph the second equation, my y-intercept is -1, 2, 3, 4, 5, but it has a slope of positive 4. And so I would go up 1, 2, 3, 4 and over 1, up 1, 2, 3, 4 and over 1. Notice they intersect at this point, which is the point 2, 3, the same point that we had before as our vertex, but we can't have this. This is not a function right now if I have both the v that opens up and the v that opens down. And so if I were to plug in a point like, let's say x equals 0, then I would have 2 times 0 is 0, minus 4 is -4. The absolute value of -4 is 4, times -2 is -8, and -8 plus 3 gives me -5. That's going to give me this point. And all of these points down here would be the points that I would get when I plug them into this equation. So this part of the graph here on top really wouldn't be included, because that part of the graph would only be considered if the a value was positive. And we know that because the a value is is negative, that it's going to be this part of the graph that opens down. I'm going to review that process again with this equation. This equation we'd need to start by subtracting 2 from both sides. So we would actually end up with y equals 1/2 times the absolute value of 2x plus 6 and then minus 2. And I think the easiest way to graph these is to first use those tricks that we found earlier. I can find the vertex by doing -b, that's -6 over 2, that's -1, 2, 3, and then minus 2. So our vertex is right here. Then I know that it's going to open up because the a value is positive, and the slopes are going to be 1/2 times 2, which is +1. And so I'm going to go up 1 and over 1 in this direction, and up 1 and left 1 in this direction, and that's what my graph would look like. And if I wanted to find the two linear equations that would determine this slope or this absolute value graph, I could simply write this equation here by changing the absolute values to parentheses and write it as 2x minus 4, and then I could do the same thing, write a second equation, but change what's in the absolute value to -2x plus 4, and then put it in slope-intercept form to graph it. and I know that it would be the part that opens down because the A value is negative. Hopefully this helps, and we will see you tomorrow in class.